Thank you for coming to the YouTube channel, Mr. Professor, or 교수 아재 in Korean. In this video, I'm going to talk about the line graph of a complete graph. So what is a line graph of a graph? The vertex set of a line graph of a graph is actually the set of edges of a graph G. So for example, if you think about the path with the three vertices, so this is P3, then you can see there are two edges. So let's label E1 and E2 in here. So if you think about the line graph here, P3, okay, then, well, there are two vertices in here, E1, because we consider each edge in a graph, okay, as a vertex in the line graph. So E2, okay. And then how can we give an edge in a line graph? Okay, so if two edges in a graph share a common end vertex like this, so E1 and E2 share a common end vertex in here, then we give an edge, okay, between the corresponding two edges or two the vertices in here in the line graph like this. Okay. So actually, in this video, we're going to talk about the planarity of the line graph of a complete graph with n vertices. So is the line graph of a case of n planar? The answer is yes or no, because it depends on n. So assume that n is less than or equal to 4, and we are going to show that the line graph, L k sub n, is planar. So we should find the planar depiction of the line graph of k sub n for n is less than or equal to 4. And n is, okay, so n is equal to 2. So that's k2 in here. And the line graph, okay, of k2, because there is only one edge in k sub 2. So if you think about the line graph, then there is only one edge. So this edge actually. Okay, so this is LK2. So it's a planar depiction of the line graph of K2. So n is equal to 3. Okay, the K3 looks like this. And there are three edges there. Okay, so the line graph of K3, okay, so because we have three edges, okay, so three vertices also in the line graph, okay, and each edge, each edge actually share end vertices with the other two edges. So we also have this situation. So the line graph of K3 is also the line actually isomorphic to K3, which means the line graph of K3 is also planar. And n is equal to 4, the K4 looks like this. Okay. And you can see there are 6 edges, and each edge share end vertices with 4 different edges actually. So if we label the edges this way, so E1, E2, E3, E4, E5, and E6. Okay, then the line graph, okay, the K4, okay, so you can put the E sub 1 in the middle and here. And E sub 1 is adjacent to E sub 2, E sub 3, and E sub 4, and E sub 5 in here. Okay, so we're trying to find the planar depiction, okay? And in this graph, you can see E sub 2 share the end vertices with the E sub 1 and E sub 3, right? And also E sub 4. Well, you can draw like this, but maybe I wanna change this one, like E sub 4 and E sub 5. So it's easier to draw this way. I mean, to have a planar deflection. And okay, and the E sub 2 is also adjacent to E sub 6, but okay, maybe I want to put E sub 6 maybe here. Maybe E sub 6 in here, so like this. Okay, and we know that E sub 3 is also adjacent to E sub 5. Okay, and also E sub 6 in here. Okay, and E sub 5 is also adjacent to E sub 4, and that's also adjacent to E sub 6. And the E sub 4 is also adjacent to E sub 6. So we have a planar deflection of the line graph of K4. So we can say that the LK sub n is planar for n is less than or equal to 4. Now let's check the case n is greater than or equal to 5. Actually, we want to show that the line graph, okay, of a K sub n is not planar for n is greater than or equal to 5. So we normally use the Euler's formula. Actually, the inequality is derived from Euler's formula to show that some graph is not planar. So like this. For any planar graph with n vertices and m edges, then we know that the number of edges at most 3 times the number of vertices and minus 6. Okay, so to use this inequality, we also should check the number of vertices and number of edges of the line graph of K sub n, like this. So how many vertices in the line graph of K sub n? Well, as I told you by the definition, okay, the vertex set of the line graph is actually the set of edges in the graph. So we know that the complete graph, the number of edges, this one is equal to this one. So that's why the number of vertices of the line graph K sub n is equal to n times n minus 1 over 2. And for each edge in the complete graph, actually, okay, and there are n vertices, okay? So if you think about the one edge, if you consider this edge and here, then each vertex is adjacent to actually n minus 2, including this one actually n minus 1. Okay, so except this one, there are n minus 2 edges from here, and also similarly also n minus 2 edges coming out in here. What does this mean? This means that every edge in case of n share common vertices actually with the 2 times n minus 2 edges, okay, which means the degree sum, okay, the degree sum of the line graph of K sub n, okay, because this is the degree of vertex in the line graph of K sub n. You can see, okay. So this is the degree of every vertex in the line graph in here. And how many vertices there? So there are this many vertices here. Okay, so this is the degree sum, which means that 2 times the number of edges in the line graph. So by just applying the previous inequality, okay, so we actually want to compare the number of edges. So you want to divide by 2. So that's the number of edges. And the 3 times number of vertices and minus the 6 one here. Okay. Well, so you can just think about the difference between those two. But because there is a 2 on the bottom, okay, so maybe you just multiply 2. So we can have like Fn. So this is just a difference. Okay. Okay. If the line graph is planar, then what happens? Then this is less than equal to actually 0, right? Because it's from here, this is number of edges, this number of vertices is actually in here. So we want to, if this is a planar, then we have this inequality actually, right? But if this is not planar, okay, then definitely we actually have this situation. and this is bigger than 0. So if we can show that for n is greater than equal to 5 and fn is bigger than 0, then we're done. You can actually simplify this one like this. Okay. And then what's our goal? As I told you, we want to show that this is a positive for n is greater than equal to 5. Then we show that, okay, the line graph is non-planar. Okay. So plug the numbers 4 into n, then you can check that's just 0. Okay, that's just 0. So okay, maybe we have something like this. So here is a 4. Okay, if you plug 4, then we have 0 in here. Okay, and then our goal is actually to show that this is increasing in here. So if this is increasing from 4, okay, from 4, okay, then this is always positive. Okay, so then we're done. Okay. So to show that the function is a positive or increasing, okay, what do I have to do? So you should think about the derivative of that one. I know, so that actually domain is just kind of the set of positive integers, okay? But maybe you can consider, okay, n as like a variable, okay? And then you can think about the derivative actually. So if you differentiate this one, then you will have 3n squared minus 12n plus 5. And then you can actually find the zeros of that one, okay? So basically, you can show that the if n is greater than or equal to 4, the f is increasing. I mean, actually, f prime is actually the positive for n is greater than or equal to 4. Thank you for watching.